My name is Carlos Arvilla from the National High Magnetic Field Laboratory, and I'm here to talk about Lenz's law and eddy currents. Anytime we have a current traveling in a coil, we also have a magnetic field.
That's called electromagnetic induction. The flip side of that also is true. A moving magnetic field, such as a magnet in motion, induces an electrical current in a nearby conductor, such as a copper tube or wire. That's known as Faraday's law. As you can see, when Carlos moves the magnet through this coil of wire, he's inducing a current in the wire. But it doesn't stop there. That current then generates its own magnetic field. That secondary induced magnetic field opposes the initial field, the field of the moving magnet. This is known as Lenz's law, as Carlos shows with this demonstration involving a strong magnet in a hollow copper pipe.
You can make an object fall in slow motion using Lenz's law. So here's what we're going to do. I'm going to drop the magnet into the copper pipe, and it's going to take several seconds to fall through before it finally hits the ground. Here you can hear it falling until it hits the ground. Even though you hear a sound of the magnet rubbing against the copper pipe, it is not friction that is slowing it down.
Then what is slowing down the magnet?
As the magnet falls, it's creating a current in the copper pipe. The electrons in the copper are moving.
Those induced currents are called eddy currents because they circulate like eddies in water.
As they move, they are also creating a magnetic field around them. Lenz's law states that the magnetic field created will oppose the original magnetic field. These two fields oppose each other, and so the magnet, being repelled, will fall in slow motion.
Let's take a look at this again. This time we're using a special green paper that allows us to see the field of the magnet, as shown here. Look for the line projected onto the green paper by the downward falling magnetic field.
3, 2, 1.
Remember, the magnetic field created by the current will oppose the field of the magnet. That induced magnetic field will pull the magnet up from above as well as push it up from below. So a magnet that would normally hit the ground in a split second falls for about 7.5 seconds before it hits bottom. These metal hoops provide another illustration of induction and Lenz's law.
On my right, I have a complete closed circuit. When a magnetic field is introduced, we have an electrical current and a magnetic field that will repel against the original magnetic field. This is Lenz's law.
As Carlos illustrates, the closed loop moves away from the approaching magnet. That's because the current being induced in the closed loop generates a magnetic field that's opposing the bar magnet's field. That secondary magnetic field circulating around the loop is repelled by the approaching magnetic field. If you could see all these forces at work, it would look like this. Notice, though, that when Carlos tries this trick with the other loop, it doesn't work. That's because the loop is broken, so the moving magnet cannot induce a current around it.